It's very common in physics and engineering to need to describe something spinning or rotating. It could be in the engine of your car, it could be your tire or wheels, it could be a planet or a star or a gear. So we need some sort of formalism, some sort of mathematics for describing rotation. So let's begin by thinking about a disk, because that's easy to think about. So here is a disk, and we specify the rotation of the disk, its position in terms of an angular position. You imagine a line drawn on it and specify an angle, say theta 1, specifies the position of that disk as it spins. So we're imagining this disk is spinning around like this, and that line tells us where that disk is. Maybe sometime later, that disk, that line is at some other angle, theta 2. And that's the angular position of the disk. And so as this disk spins, that line goes around, and as we know where that line is, we know the angular position or the rotational position of the disk. Now, if we want to know how rapidly the disk is spinning or rotating, then we want to know how rapidly that angle is changing, and that is something called the angular velocity. So angular velocity is the rate of change of angular position. We give this the symbol omega. It looks kind of like a W, but it's the Greek letter omega, so it's kind of curved rather than the straight sides of a W. So omega is theta 2 minus theta 1 over T2 minus T1, or just delta theta over delta T. It's just how rapidly the angle is changing. That is called our angular velocity. Its units are units of angle or units of time, and we have to specify here our angle in radians, not degrees, but radians per second. Now, sometimes we need to be able to relate how rapidly something is spinning in angle to how rapidly something is actually translating, how rapidly something, say, on the disk is moving. So suppose I had a point on this disk here, and I want to actually know how fast in just regular velocity it's moving, how fast its tangential velocity is. And to do that, we have to have a relationship between the linear variables that we're used to using and the angular variables. And to do that, we need to know actually what radian measure means. So here is our disk again. Here's an angle theta. The definition of theta in radians, if this is radius r, this is arc length s, and by definition, theta in radians is, by definition, theta in radians is s over r. It's arc length over radius. So if we want to know, for example, the arc length, you can multiply through. Arc length s is r theta, provided that theta is in radians. Notice that radian is a dimensionless measure. Arc length is in meters, and radius is in meters. So radian is a meter per meter. So sometimes that will help us in seeing the unit radian may appear or disappear. We'll see what that means later. So this arc length s is r theta. So if this is a disk that's spinning, and we go from, say, one angle to another angle, so that this s changes by delta s, and this theta changes by some delta theta, then we've got delta s is r delta theta, because the radius didn't change there. If I divide both of these by time, delta s over delta t is a velocity. It's the velocity along the arc here, it'd be the velocity of a point on that disc, a bug sitting on the disc. If this were a merry-go-round, it'd be a velocity of someone sitting on the merry-go-round. If it's looking down on a planet, it'd be a velocity on the edge of the planet there. So this is just our velocity, v sub t. I'm putting the t there for tangential. Tangential velocity is just r times delta theta. Delta t is our angular velocity. So v is our omega. This allows us to relate this new idea, this angular velocity, to the velocity that we're already accustomed to, this older idea. So for example, suppose I have something that's spinning at 20 radians per second and has a radius of 4 meters. Then, so it has omega is 20 radians per second, radius is 4 meters. Then a particle out here at 4 meters would have a tangential velocity of r omega, would have 4 meters times 20 radians per second, would be moving at 80 meters per second. Notice my units would be meter radians per second, but radian is a meter per meter, so I can just let that radian go away, and my units are still true. Now, quickly, there's another unit that sometimes comes into play here that's so important, I have to mention it and show it to you, because it's so very common. There's another unit of angular velocity that's called the RPM. So RPM. RPM is revolution per minute. Revolution means exactly what you think, going all the way around. So revolution is when you go all the way around. So revolution per minute is how many times something spins every minute. So this is the unit that's in your car. Your tachometer on your car tells you how many times your engine turns around every minute. So a common RPM in a car is about 2,000. So for example, in your car, you might have an omega that's 2,000 revolutions per minute times one revolution going all the way around is 2 pi radians. So you've already learned that all the way around is 2 pi radians, which by the way is also 360 degrees, just in passing. So 2,000 revolutions per minute times 2 pi radians per revolution times a minute per 60 seconds. So that number in your car of 2,000 revolutions per minute, let's see, that's 2,000 times 2 times pi divided by 60 is 209 radians per second. So this is the number specified on your display, 2,000 RPM. If we needed to use that number in a calculation, in a physics calculation, we would have to convert it to radians per second. Now, so we've seen position, theta, angular velocity, omega. We also, when we were first learning our physics, we learned about something called acceleration. There's also an angular acceleration. So if our disk is speeding up or slowing down, then omega is changing. So we can have an angular acceleration This is the rate of change of angular velocity. We give it the symbol, instead of A for acceleration, we give it the symbol alpha from the Greek alphabet. This is omega 2 minus omega 1 over T2 minus T1, or delta omega over delta T. That is our angular acceleration. So if something, for example, slows down from some omega 1 equal, I don't know, 40 radians per second to some omega 2 equal 20 radians per second, and it takes 2 seconds to do that, then that would mean alpha is omega 2 minus omega 1 over T2 minus T1 is delta T. So that's 20 radians per second minus 40 radians per second over 2 seconds. 20 minus 40 is minus 20, over 2 is minus 10. So this is minus 10 radians per second every second, or minus 10 radians per second squared. So that would be our angular acceleration. So this is our introduction to how we describe rotational motion in terms of theta, in terms of omega, and in terms of these relationships that tell us how to move from one to the other, S equals R theta. In another chapter, we're going to have uniform angular acceleration equations, just like we had uniform acceleration equations. And so we'll get more practice with these later. So for the moment, we'll learn to use these equations in your in-class and in your homework. So see you soon.